for me, I see dark blue, light blue, kind of red, grayish. What do you guys see? Something along those lines? Okay. All right. Now, so if you keep a sort of eye on the same blocks, okay, I'm not going to change those blocks. I'm going to shuffle around the rest of the blocks. Okay. What do you see? For me, at least, I see all of them to be kind of grayish. I don't see them now, blue and red and so on. Now, if I actually arrange corresponding colors next to them, I kind of start seeing them to be more related to the color next to me. So it's very interesting that our ability to perceive the color actually is not just based on the actual color, right? Because in this case, I'm not changing the light source. I'm not changing the illumination spectrum in this room. But what you are changing is the neighboring relationships or neighboring colors. So what I'm sensing in terms of color is also kind of dependent on what my neighboring colors are. Now, which is a very interesting perception problem, or quality of this. And partly because we are generating color representations based on dependency relationships. We don't expect that things change in color space dramatically. We expect that there is some notion of constancy. There is some notion of continuity of color. And of course, yes, there can be dramatic changes, but those happen under scenarios where I cannot ascertain or enforce a constancy model. So in this case, I perceive this to be gray. I don't see any constancy around it. So this is kind of like edge detection, except these are gradients in the color space as opposed to purely in intensity space. Now, what are the uses of color actually in computer vision? Right? So how do we use them in our processing and computational properties? And so the use of color started out kind of late, primarily because we didn't have that many color sensors around. But 90s came around, color sensors started appearing. We started thinking of how to use color. And the first use of color was relatively simple in the sense that, well, I'm getting RGB values out of my sensor. So let's just use RGB values and do something with it. Right? So how do I apply color in order to associate objects or regions of different objects? Okay. So I look at RGB values, I can construct a histogram of RGB values, and anything else having a similar histogram of RGB values, well, maybe they are the same. Right? Because, well, integrally they look like their appearance is same, so they must be the same. So that was kind of the first use of color histograms in trying to index and retrieve objects that were similar to each other. Great, and this was all based on RGB histograms, right? Later, people actually said, well, this is interesting. We can use these kind of models to design representations for physical structures. For example, skin. Skin should have a unique color representation. People tried doing that and applied it for segmentation and things like that. And, well, it was okay. It doesn't work very well, but it was applied and interesting results and formulations were found. And of course, we use color, of course, now in a variety of ways for solving fundamental image segmentation problems and so on and so forth. And you are seeing now, of course, color being used a lot, right, in variety of formulations. But some of these are very early formulations, and some of the ones where how color representations have evolved over the years. In fact, I don't know if you guys know of this competition called RoboCup. It's basically robots playing soccer. And over there, I mean, everything is a lot of it is driven based on color. Right? Because you're trying to get the ball into the goal, and obviously you don't want to confuse the ball with everything else. So the simplest and fastest way of getting the reaction out of a robot is to say, here's my scene, find the ball. Right? The ball is always the same color. So easiest is color segmentation. The problem is, the fundamental problem over here has been color is the perception of that color will change depending on what shadows fall on that, depending on how the illumination environment is, and so on and so forth. Right? So if you go back to sort of papers referring to RoboCup, the earliest models where you know the color of the ball, who trained the model for it, not like they went out in the field, they completely collapsed. Right? Because they're trained on what would be images of this, but you go into a corner somewhere, or other robots are surrounding the ball, and I don't see the color in it. So there's a big change in color. In fact, 3 years back, there was a more recent paper on trying to build color models where people said that, well, it's impossible to build a color model that seems to stay constant under all the different illumination parameters. And unfortunately, I don't have time in RoboCup to go and solve for a wonderful, albedo model. Right? Ideally, that's what I would like, to call the albedo. But I can't do that. I don't have time because it does for all those wonderful illuminations. So people have gone out and created what they call ensemble color models. So they say, I can't find a single transformation that gives me the same color representation and the different illuminations. So go and create representations under all possible illuminants, and I create an ensemble representation. Anytime I go into that ensemble, we get a match. And well, they said, okay, they could do a little better. Yes, there are. But again, yes, there are. And that's what we typically use in order to reason a little bit about constancy of color. Right? But it doesn't necessarily translate very well to physics. Keep in mind, all of those models work very well when you have a simplified color model, right? Keep in mind, we have a simplified color model expressed based on primaries. All of these are derived from that. If you come into a real environment, you are going to have color which is not only based on primaries, but everything else in the world, which we have not accommodated. So, under primaries, we have a perfect model. Perfect as, you saw the model, right? We have, variations in color are not necessarily perfectly normalized, they're not perfectly Euclidean, we approximate that. But now you add the complexity of, the effect of spectral radiosity from all the other options. That we don't have an explanation for under the primary model. Okay, now, so there are multiple, large number of papers, right, which basically have used color and show how much we can do with color. And the reality is we can do quite a bit. In fact, it's very interesting, some of the more recent work has actually used color more in terms of constancies to ascertain whether, this is actually a falsification or an artificial image being generated as opposed to something that's natural. And it's very interesting that you can actually use these constancy models to understand that. Okay, so let's come back to our typical sensed values of color on a digital sensor or a digital image. So what we have is RGB color space, right? So what is the RGB color space represent, right? It represents three axes of color. Keep in mind we typically represent them as being independent values. And of course you have within that the cuboidal representation, because each value goes from 0 to some value, 8 bit is 255, right? So I have three axes, and the result now I have a cube, which is